Hey everybody, this is Mrs. Adiemeyer, and we are going to be starting to talk today about some of the things that go on the interior part of the atom. Specifically, we are going to be talking about giving the electrons a little bit more specificity. And what I mean by that is kind of knowing where our electrons go in our atom and how they're arranged. And knowing those things is going to really help us in our next unit when we need to be able to predict the properties of how elements are going to bond together. So before we know how things are going to join together, we need to know how they are arranged individually, and then we can go from there. So we're going to start off today by talking about photoelectron spectroscopy and how that lets us know information about what's going on inside the atom. So most of you guys are probably familiar with the classic model of how electrons are arranged outside of the nucleus in any given atom. And that model is called the Bohr model. And we will use this kind of over and over again because it makes things simple. But I want you to know that you're going to find in this class that everything that you kind of learn the first time about the atom gets a little bit more complicated in this class. So you are going to notice layers of complication, I guess would be the best way to explain it, as we go through further and further into class. So anyways, the Bohr model is kind of the classic model that we talk about when we talk about electrons in atoms. And the way that it works is that we call our locations for our electrons electron shells. And there are kind of specific numbers of electrons that can fit into each shell. So the first ring kind of around, or electron shell that we call it, around the nucleus can hold a maximum of 2 electrons. And then the second shell here can hold a maximum of 8, and the third shell can hold a maximum of 18, and it kind of keeps growing from there. Now, the reason we teach you that is because atoms aren't anything that we can actually see, and this gives us kind of a nice, simple model. But the reality is that things are a little bit more complicated underneath the surface. Each of these shells, if you want to call them that, are technically called an energy level for an atom. So an energy level and a shell are essentially the same thing. And then what actually happens is that within the shell or energy level, there exist these things called subshells. So if you think about an energy level being like kind of the big area, a subshell further divides that big area into other places where electrons can hang out. And scientists theorize that those places exist, and they use a technique or a method called quantum mechanics to kind of predict where those electrons were going to lie. And eventually what happened is technology kind of caught up with the theory, and they were able to use a technique called photoelectron spectroscopy to be able to confirm that that exists. So what photoelectron spectroscopy does is it gives us kind of an idea about the inner workings of the electrons in a given atom. And how it works is that it takes advantage of an occurrence called the photoelectric effect. So the photoelectric effect works with the idea that if you take any kind of sample of an element and you hit it with enough light at the right energy, you can actually take electrons and force them off of the atom. So it kind of like rips the electrons off of the atom. And what you can do is you can pay attention to the ripped off electrons. And when you do that, it gives us information about the internal structure of a given atom. So what they do is they shoot what we call photons, which is just a fancy name for basically like particles of light or electromagnetic radiation. And what they do is they shoot that source at the sample. You can kind of see it here. And when the energy is right and they hit the atoms with enough energy, electrons go flying off. And when they go flying off, they collect them in this energy analyzer. It analyzes how much energy those electrons have, and it gives us an idea of how strongly the atom is holding on to those electrons, how far away they are from the nucleus, and all that kind of stuff. Now, the photons that are being shot at that sample are either going to be ultraviolet light, which you guys probably have heard of, or X-rays, and both of those are high energy lights. So it does take a lot of energy to rip those electrons off of the element. And what ends up happening is after those electrons go through the energy analyzer, what happens is you get some data that's processed by a computer, and eventually it gets put out into a graph that contains two things. So what you're going to have is you're going to have something called the binding energy, and that's going to sit on the x-axis, which, if you remember, is the horizontal axis on your graph. And the binding energy is how hard it is to take away the electrons. So the higher the energy value, the harder it's going to be to take those electrons away. The other thing that it's going to show you is the relative number of electrons that have that energy. And then what to look for on those charts. And we are going to be going through a bunch of this information, and we'll practice a bunch of examples, so there's not too much to stress about. When you take a look at a graph, each peak is going to represent a different type of subshell. Okay, and there are 4 different subshells that we are going to encounter. The S subshell has a maximum capacity of 2 electrons. The P subshell has a maximum capacity of 6 electrons. The D subshell has a maximum capacity of 10 electrons. And the F subshell has a maximum capacity of 14 electrons. So kind of keep that stuck in your head for later. Okay, and then when we look at our graph, the peak height is going to show us how many electrons are in that subshell. So we are going to go through some examples, and hopefully that will make things a little bit clearer. All right, so this is, struggles there. Example number 1. So this is an example of a spectrum that you're going to get for a PES diagram. So like I said, you're going to see energy on the x-axis. When you pay attention to this, higher energies mean it's harder to take away electrons. Lower energies means it's easier. So it's harder to take an electron away if it has a high energy, and it's easier to take an electron away if it has a lower energy. Okay? With that in mind, electrons that are closer to the nucleus are harder to take away. Okay? So when we're looking at our energy values here, and these peaks that you see, these little spikes, the ones that have a higher energy are the ones that are closer to the nucleus. So what we're going to do is we're going to be asking you to kind of go through and analyze these spectrums and tell us what they tell you. So this is the PES diagram for lithium. And if we find lithium on our periodic table, Li has the atomic number of 3, which means that lithium has 3 electrons total, okay? So when you see these little spikes on a PES diagram, what they represent is a subshell, okay? So this is a subshell, and this peak represents a different subshell. When we look at these, the height of the peaks show us how many electrons are in there. And what we have to do is we have to compare sizes. So we know that lithium has 3 total electrons, and this first peak here has twice the size as the second peak. So what that tells me is, since I have 3 electrons and this peak is twice as high, is that this first subshell has 2 electrons and the second subshell has 1 electron. Okay, hopefully that makes sense to you, but we're going to go through a bunch more examples to make sure things are really solid. The other thing I want you to know is that the peak on the left here has the highest energy because it's close to 10, and this is less than 1. So this first peak here is the electron subshell closest to the nucleus. Okay? So when we think about our electron subshells, and you kind of think about those layers of electrons, our first layer of electrons has 2 in it, and our second layer of electrons has 1 in it. Okay, so the first subshell has 2 electrons, the second subshell has only 1 electron. So that's example number 1. Okay, example number 2. You should pause the video and see if you can give this a try. So pause it, give it a try, and we'll go over the answer. All right, to boron. Boron has an atomic number of 5, which means that boron has 5 electrons. Okay, we'll find first the peak closest to the nucleus. We find the peak with the highest energy. So if we look here, highest energy peak is going to be this peak here. So this is closest to the nucleus. Okay, now if you look at our peaks, we have 1, 2, 3 peaks this time, and 3 peaks, 5 electrons. These 2 peaks have the same height, and this one is half the height. So in my mind, I think about, well, if these 2 are the same height and this one is 1 less, this probably is only 1 electron here on the outside, and these 2 peaks here are probably 2 electrons because they are the same size. So when you think about this, our first subshell closest to the nucleus has 2 electrons. The second subshell has 2 electrons, and the third subshell, which you can see is very close to the second one, has 1 electron in it. Okay? All right. Example number 3 is oxygen. So what I'd like you to do is pause the video and see if you can figure out how many electrons are in each subshell here, and then we will go over them. All right, oxygen. Atomic number 8 here. So 8 for our atomic number means that we have 8 total electrons. Okay. Our closest peak to the nucleus, or our closest shell to the nucleus, is represented by the highest energy. So we have a number under 100, and then we have a number under 10, and a number close to 1. So this peak here is closest to the nucleus. Okay, and we have 8 electrons. So if we look, this is our first shell here, our second shell, and our third subshell. So we've got our 3 subshells for oxygen. And then the peak height here, I kind of wrote over it, so that's not good. But the peak height is about twice as big for this third subshell as it is for the second one. So if you think about our electrons, we've got 8 total electrons here. If this peak is as big as these 2 peaks combined, that means that I probably have 4 electrons in my subshell that's on the furthest out. And then each of these little guys has 2 electrons in them. So it's 2, 2, and 4. So in oxygen, my electrons are organized with 2 electrons in the first subshell, 2 in the second, and then 4 in the outside one. Okay? And the last example. This one gets a little more complicated. This is for aluminum. So if you want to pause this, see if you can figure out how many electrons are in each of the shells, and then, or each of these subshells, and then we'll go over it. All right, we will find aluminum. Aluminum has 13 electrons total. So we've got to kind of pay attention to our heights here. We also maybe are picking up on some patterns that you're seeing. So hopefully you're kind of picking up that on these graphs, this is our closest to the nucleus. Okay, so that's the closest shell or subshell to the nucleus. In this case, we have 1, 2, 3, 4, 5 subshells. So aluminum must be, a pretty big element here. And if we look at our peaks here, these 3 are all the same. This one on the very end is a small little peak. And then this huge peak here is 3 times the size, okay? So if you kind of remember what we talked about with our subshells, there are some common numbers that you start to see. The S subshell can hold 2. The P subshell can hold 6, and so on and so forth. So what you are hopefully kind of starting to see is some patterns here. Now I've got 13 electrons. This peak is really high and about triple the size. these first two peaks in every element that we've talked about had 2 electrons and 2 electrons. That pattern still follows with aluminum. And if we think about this peak size here, it is about triple the value. So there are 6 electrons in this subshell, 2 electrons in this subshell, and then another one hanging here, okay? So what we have are 5 subshells that are varying distances from the nucleus. Okay, so this is one subshell, another subshell, another subshell, another one, and another one. These make up those overall energy levels or shells that we talked about. So what I'm going to be asking you guys to do in the practice and the practice understanding check as well is to kind of go through and see if you can predict what these peaks represent and how many electrons they have. In our next video, we're going to be going through and talking about how these things relate to giving the electrons a home within the element and being able to identify that home. If you have any questions, please make sure that you show up to a Google Meet and we'll get things cleared up as soon as possible. Good luck.